Okay, so welcome everybody. Today I'm going to discuss our study on puck possession in the NHL. So before we get into it, I'm going to give a little teaser here. So later on, you'll see that we found a metric of possession that's highly correlated with team success. And in fact, it's also predictive of team success, so for future success. And it's on par or perhaps even better than existing metrics or expected goals models. So we'll get into that, but let's first provide some background. So why did we study team possession? Well, several reasons. The first is that it's an attempt to identify a reliable metric that genuinely influences team success. Second, we find it's interesting to see where hockey fits in the possession debate across sports. Many people think that if you outpossess your opponent, you're going to score more goals than them, but actually results in studies in other sports vary widely. Some studies show that possession matters, and some show that actually it's not correlated to success. And lastly, we now have an actual player possession model from the NHL, albeit unofficial. And so this data will allow us to test these hypotheses. And also, it's the first use of this player possession model to our knowledge. So by leveraging the data, we can improve it through feedback. And also, we can set up future research if we clean it and process it in a way that now we have a validated possession model, so people can use it going forward. Okay, so as mentioned, this work was made possible from advancements in the NHL's puck and player tracking dataset. So in March 2023, a new player possession model was introduced. And specifically, it was introduced into the DISH data stream. So this is a different data stream that features delayed, interpreted, smoothed, and 100 hertz enhancements. And so in order to use it, we merged it with a game information file and then performed several cleaning and filtering steps. And so the steps in which we did this are explained in great detail in the paper, as it's one of our main contributions to be able to clean and use this data for other researchers going forward. So as mentioned, that's our first contribution. We developed a robust methodology for cleaning and processing this NHL player possession data. And secondly, we examined correlations between various possession indicators and metrics of team success. Thirdly, and most notably, we introduced our new metric, average offensive zone possession time differential, or average OZPTD, or OZPTD, depending on which way you say it. And we show that it's highly correlated with team success, and we also highlight its potential as a predictive tool. And lastly, as we posit this new metric, we evaluate it to ensure that it's stable and that it can be used, and it's contributing unique insights compared to other metrics. Okay, so we're going to get to the OZPTD, but before we do so, I think it's important to figure out, what exactly did we get from the NHL, and then how did we modify it in order to use it? So this is what we get from the NHL. So A1, A2, and A3 are players on Team A, and B1 and B2 are players on Team B. And so what you see is what we got. We basically only know who has the puck and for how long. So we know the start and end time of each player possession. And so in order to use this, we merged it with a game information file, as you see here. So that told us when stoppages occurred. And so now we can compute these orange dotted lines, which is basically periods that nobody had the puck. And also, this is where we found some truly erroneous possessions. So some, lasted as long as 20 minutes because they incorrectly went into the intermission. And so by merging it with the game information file, here we can actually do a lot of the cleaning and filtering. We can stop possessions before intermission occurs because nobody possesses the puck for 20 minutes at a time. Okay, so now we have validated and modeled individual player possessions. We know who has the puck, and we can have a good sense that it's actually occurring for this amount of time. And so then the next thing we did is we computed team possessions, as you see here. So now the green dotted line shows periods that no team had the puck. And as you can see, our definition of team possession is the aggregate of individual player possessions. So basically, as long as players on the same team, interchange and possess the puck, the team possession continues until the other team gets the puck or until a stoppage occurs. Okay, so now we have a model of team possession. Hopefully you can understand it. And I think something that's important to us is that team possession is something that everybody can understand. And so now hopefully we all do. And going forward, we're going to show how it's relationship to team success, because I think, the intuition is that if a team has more possession than the opposing team, they're likely going to score more goals. And because their opponent has the puck for less amount of time, they're likely going to get less opportunities to score. So let's actually look at that relationship here. So here you can see, when compared to metrics of team success, so the correlation between team possession percentage and average goals for is a moderate 0.56. And when you compare it to average goals against, so you would think, if I have the puck more, then the other team has it less, and then therefore they're going to score less goals. But it's actually a weak correlation of negative 0.38. And same with goal differential, it's a moderate correlation of 0.56. And so I just want to note here that the data set for this relationship and all relationships going forward is the first half of this NHL season. And I also think it's important to note that you might think to use the metric of success as wins or points per game, because that's what ultimately matters to every team. But we instead use these three metrics of team success because they're adaptable to different contexts. So for example, later in the paper, we're going to talk about how we want to use just even strength situations. And we can compute goal differential only for even strength. And as well, it's highly correlated to team success, to points per game, has a 0.95 correlation, so it's a pretty good proxy. Okay, so I'm throwing out a lot of correlation numbers here and a lot of jargon, so I think it's important to take a step back at this point and explain how we interpret correlation values. So this is our interpretation. So a correlation value like 0.95 between points per game and goal differential indicates a very strong correlation. And so that, is inverted for negative numbers. If things are negatively correlated between negative 0.9 and negative 1, that implies a very strong negative correlation. So you can think of the correlation between goals against and wins. As you get more goals against, then you probably get less wins. So those are highly negatively correlated. And so then going down the list here, a 0.7 to 0.9 correlation we deem as strong, 0.5 to 0.7 is moderate, and then below that, you have weak and none to negligible correlations. So if you're in those two categories, there's nothing to write home about. Okay, so taking it back to this, you can see that the correlations are only moderate, or in some cases for goals against, it's weak. So we were a little bit bummed here because, it's failing our intuition. So we decided to dig a little bit deeper and look at only offensive zone possessions. So here is where our new metric comes into play, average OZ-PTD. And the idea is that we can remove defensive and neutral zone possessions because those might serve to facilitate transitions rather than, directly to scoring goals. When you possess the puck in the offensive zone, that's when you score the goals. Not many are scored from the neutral zone. And so we just remove those possessions, then look at offensive zone possessions. So let's break down this acronym a bit more, and I'll do so with a diagram. So this is how we calculate OZ-PTD. It starts with this diagram, which shows the goalie for the blue team is on the left side of the ice, and the goalie for the red team is on the right side of the ice. And so then that means that the right side is the blue team's offensive zone. So let's say for a given game, the blue team has 10 minutes of offensive zone possession. And that means the left side is the red team's offensive zone. So for this game, let's say the red team had 8 minutes of offensive zone possession. And so then I think you can see where this is going. To calculate the blue team's OZ-PTD, you take 10 minutes minus 8 minutes, and you're left with a value of +2 for the blue team. So that means that they spent 2 more minutes of offensive zone possession than their opponents did. And conversely, for the red team, the value is -2. So I'm just going to pause here and say that this is really important for us, that this is understandable to all stakeholders, so coaches, players, and fans, so that you can communicate it effectively, and so that it can actually be used in practice. So hopefully it's understandable. And so when we calculated this value, OZ-PTD, for every game and for every team, and then checked for its correlation with team success, we got much stronger numbers. So now you can see that the correlation between OZ-PTD and goal differential is 0.77 for our data set. So if you remember back to our correlation interpretations, that's a very strong, just a strong correlation, but safely in that bucket. And so we're going to dive deeper into this relationship because we think that, it's an interesting insight that this is a strong correlation. And so we're going to do so first by showing this graph. So on the x-axis is the average goal differential, and on the y-axis is the metric that we calculate, average OZ PTD. And every point there on the plot is the team's value. So they have an average goal differential and they have an average OZ PTD. And so the top right quadrant is kind of where you want to be. That shows that teams that have high average OZ PTD typically outscore their opponents. So think of teams like the Oilers, Carolina, Colorado, and Florida. And the bottom left shows you that teams with low average offensive zone possession time differential typically get outscored. So their opponents score more than they do. And there's also a couple interesting teams to note here. So the Bruins had a negative OZ PTD. So that means that on average, their opponents spent more time with offensive zone possession than they did, but yet they achieved a largely positive goal differential. So I'd like to speculate as to why that occurs, but my advisor, Tim, tells me that as a researcher, you're not allowed to speculate. So I'm not going to do so right now, but maybe if you come up to me at lunch, we'll see. Okay, so I'm going to pause here for a second. And so, we showed a couple graphs and we can see there's a strong correlation, but you might be thinking, well, what about the effect of power plays? If a team has many more power plays than another, they're going to obviously have more offensive zone possession time. So we accounted for that by removing power plays here. So this is where it comes into play that we can, use goal differential instead of wins. So on the x-axis now is the average goal differential only for even strength situations. And the y-axis is average OZ PTD, again, only even strength. And here you can see the correlation remains high at 0.73. So clearly this relationship is not just a byproduct of power plays. The importance of offensive zone control is shown throughout the game. So now that we showed it's strongly correlated within sample, let's look at some out of sample and how predictive this metric is. So to do so, we fit a linear regression model using just a singular input. So we split the data set in half. We used OZ PTD and goal differential for that first half to develop a relationship, and then used the average OZ PTD in the second half to predict goal differential. So that might have been fast. Let's go a little slower. A first half of the data set here. So it's just like we saw before, where we plotted every team's goal differential, every team's OZ PTD, and then we drew this red line of best fit. And so then for the second half of our data set, we kept this line. And then all the model does is it's very simple. It just takes a team's average OZ PTD and then finds the corresponding goal differential value. So to be clear, the model has no knowledge of the team's goal differential in the second half of the data set. It just uses their OZ PTD value to predict it. And so in doing this, we compared the predicted value with their actual value of goal differential for the second half. And the results are right there. So the R squared is 0.49. That indicates that 49% of the variance in goal differential is explained by OZ PTD. And the correlation between the predicted values and the actual values of goal differential was 0.73. So again, a little bit more jargon. So I put it in context here with some other models that we found online. So on the left, it's an article from 2015 from a popular hockey analytics blogger, DTM About Heart. And they used their expected goals model to predict goals, and they found an R squared value of 0.3. And so you want your R squared to be as high as possible. So ours was on par or a little bit better than this one. And then the middle is from Hockey Statistics, or otherwise known as our friend Lars, who's going to speak later. And so his expected goals model and also the expected goals model from Evolving Hockey, using that to predict goals showed an R squared of 0.49, so the same as our model. And lastly, on the right is a paper from MIT Sloan Conference from 2012, and they developed a model and showed the correlation between predicted and actual values was 0.69. So I think it's interesting here because you can see that these relatively complex models, our simple model of just using OZ PTD is on par or perhaps even better than these ones that we found. And of course, there might be more, but this is what we were able to find online. So we showed a strong relationship in sample. We showed its potential for prediction out of sample. So now we think it's important to rigorously evaluate this new metric. And so to do so, we use this paper by Frank Zayal, which is about meta-analytics, and I think it's a fantastic paper. And so what it does is it says that for every new metric in sports, you should evaluate it under three properties. So first, is your metric stable? So is it consistent over time? Because if you're a manager trying to make a decision about acquiring a player, you want to make sure that their past statistics are predictive of future statistics. And so is your metric stable? The second is asking what's the discriminatory power of your metric? So is it actually able to distinguish between teams or players? And also, is it able to distinguish between true variability and noise? And lastly, is it providing unique insights over existing metrics? We've seen in some sports, in some cases, there's a clutter of metrics that all kind of aim to do the same thing. So the paper talks about WAR in baseball. So that's wins above replacement, and there's many metrics that attempt to do the same thing. So the idea is to make sure that your new metric is providing unique insights. Okay, so we're going to evaluate our metric under these three properties. So to evaluate its stability, we plotted the average OZ PTD in the first half of our data set versus the second half, which is on the y-axis. And so you can see the points pretty closely follow the line, and there's a correlation of 0.84. So that validates the metric's consistency. And so, if you're using it to forecast future performance, you can see that it's relatively consistent. And so to evaluate the second property of discrimination, we plotted this graph. So on the x-axis is obviously all the teams. The y-axis is their value of OZ PTD, along with 95% confidence intervals. So that's the top and bottom of each plot. And so you can see that the range is pretty big for some of them. Like you can have an OZ PTD range of almost 2. And so that shows you the variability between games, just how much you possess the puck in the opponent in the offensive zone versus your opponent. Okay, so for discrimination, to remind you, you want to make sure that it's able to distinguish between teams. So these three that I circled there, you can see that there's those would be statistically significantly different because there's no overlap in their confidence intervals. So that's the case for some of these, but for some others, there's overlap, which means that perhaps they're not statistically significantly different. And so that suggests that this metric might be only moderately discriminatory. Okay, so now lastly, to assess the metric's independence, we looked at Corsi. So Corsi is the shot attempt differential, and it's long been used as a proxy of possessions because without possession data, you can look at the shot attempts differential, and then that tells you maybe who had the puck more. So we were curious to see if ours was independent of Corsi. So you could see the first thing we did was that we found OZ PTD is highly correlated with Corsi, a 0.83. So that made us worry that it wasn't independent, but the crucial comparison comes next what is its correlation to goal differential? So Corsi has a 0.62 correlation with goal differential. So if you remember, that's in the moderate range, but our metric, average OZ PTD, has a 0.77 correlation with goal differential. So even though at the top you could see that these two metrics are correlated, the fact that OZ PTD provides additional insights in relation to game outcomes means that it's useful and provides unique info. Okay, so I just want to remind everybody that our results are only as good as the data that we get. So these results are relying on an NHL player possession model that is currently evolving. But we think that, and we know that our cleaning and filtering process will be applicable to whatever changes are made to the model. And also, as will be the process of developing this metric and showcasing its success. And another potential limitation is that we only used half of this NHL season. And so in future work, we'd like to expand it to a full season or multiple seasons to ensure that it retains its ability to predict success. And so as for future work, we're very interested to know what the impact of individual player possessions is. Maybe are those predictive of an individual's points or goals or assists? And now the second one is in relation to just now having a possession model. And now we can look at everything as to what occurs within possessions using the NHL's unofficial player possession model. And so there's a whole bunch of interesting work to do in that space. And so to conclude, we have a rigorous methodology to clean and filter the player possession data, and we really think that'll set up future analysis. And secondly, we showed our new metric, average OZ PTD, and that it's a reliable indicator of team success, and that its potential for predictions is strong. So before we conclude, I just want to wrap with a quick hindsight here. So you might be thinking that, okay, of course, more offensive zone possession than your opponent will lead to more success. That was obvious. Why'd you do this whole presentation? Well, actually, that intuition is a little wrong. This graph shows you per game instead of averages now for the same data set. So the x-axis is goal differential and the y-axis is OZ PTD. And each data point is now a specific game. And you can see that this correlation of 0.77 completely falls apart. And so our intuition of this is potentially incorrect, and it's the fact that we averaged it and dug a little deeper that led to this conclusion and this strong result. Okay, so that's everything. I'd really like to thank everybody here for listening, especially Ben Resnick from the NHL's research and development team and Jonah Eisen from Rogers Communication. We had many fruitful discussions. They were super positive, but also gave meaningful feedback. And also to the anonymous reviewers, I hope you know I think you'll notice how improved the paper is based on your feedback. So we really appreciate it. And lastly, there's a link to the paper there if anybody'd like to see the whole detail and also to use it going forward. So thanks a lot for listening.
Questions from the audience?
Yeah, thanks. Really, really interesting. Just wondering, what about possession in neutral zone? Do you ever thought about including this, or do you think it could help improving the model? Any thoughts about this one?
Yeah, it's a good question. So the way we did it was the reason we were able to use offensive zone possessions is because we split it up into all three zones. So I don't have the exact result, but I remember that we looked at neutral zone possessions and just the same thing. So think of N, P, Z, T, T, and that correlation to team success was lesser. I don't remember the exact results, and I can get that for you, but that was definitely something we considered. And I know there's a talk later, or the student competition talk about neutral zone possessions, and I think so. I'm interested to see where that goes. And I think that talk talks about the decisions you make in the neutral zone that maybe lead to more OZ PTD. So maybe it's that facilitating transitions that you could take it a step back and get some interesting insights. Thanks.
If you were to break the OZ PTD down by position, like forward possession time and defensive possession time, do you think that would be worth looking into, or would the difference be negligible in the model?
Oh, definitely. I think it's important to note, so his question, I guess you're mic'd up, but the question was breaking it down by player position. So if forwards have OZ PTD, does that correlate to their better success versus defensemen? And so I just want to, so we use this only for team possessions. So we were just focused on team success in this paper. And so future work will definitely look at individuals' offensive zone possession and whether that leads to more goals, and same with defensemen. And so I think that's definitely going to be a part of that future work. So stay tuned, I guess. Does that answer your question?
Yeah, thank you.
Okay.
Yeah, so congrats on the paper. I thought very well done.
Thanks.
Maybe from the industry side, I can give you a couple of stories that we looked at. So at the World Championships, Switzerland was very dominant at the group stage in the last few years, and then not this year, but a couple of years before, failed at the quarterfinals. Then we had Finland winning some gold, even though not being part of the the top teams by the data, and especially not having a lot of ozone time.
Mm-hmm.
So in a finer granularity, it is also sometimes a proxy of a team quality, their ozone time. So the stronger the team, the more ozone time they will have. But it is still possible for the teams generating off the rush or off the forecheck in those settings to win or upset teams. They're less likely in a best of 7 series, but elimination games like at the World Championships, that's certainly a tactic applied, and then that kind of brings us to this outsider role of teams, where really important to be strong off the rush or not lose the rush game, not lose the forecheck game, and that maybe just some granularity to your paper. One question I have is very important in our analysis are those neutral pucks. So how do you handle like a controlled pass from player A to B? Is that considered an ongoing possession? Is that a neutral puck? Then after a shot, say the offensive team retrieves the rebound, does that count toward the possession time, or is it a neutral puck every time? How do you handle that?
Thanks a lot for the question and for the insight. I think that the first thing about the comment about how, Switzerland, for example, or Finland, I think it was, dominated possession and shots, but they still lost. Is that what you said?
No, so Finland was super successful, won a couple of goals despite not having much ozone possession. They were really strong off the rush, just won the rush game and the forecheck game, and most of the goals are still generated off the forecheck, off the rush, which would be very little time in the ozone. Yeah,
and so the different strategies of teams is super interesting. We just saw a couple nights ago, the Oilers in the NHL playoffs got outshot 31-10 by the Stars, but yet they won and they're moving on. And so I think that kind of, makes me think of this graph where if you look on a game-to-game basis, hockey's random. So if you outpossess your opponent, there's different strategies that lead to success. It's not necessarily going to work on a per game basis, but the idea is that over time, over a whole season of data, your strategy of outpossessing your opponent has been one that we saw in this NHL season to be successful. But I think that the importance of different strategies and teams that are able to contribute off the rush is for sure something I'd like to consider. And the second part of your question for neutral zone possessions and for rebounds, so there's a little bit of it.
Neutral pucks. It's just I saw the filtering, and I know that takes a lot of work because we kind of have to deal with the same issues. And just how you handled that, because we made some rules on how it is still an ongoing possession, even though a pass occurred, and then just how do you handle that after a shot and so forth. But that's regarding ozone still, not the neutral zone. It's a neutral possession state, I would say.
Yeah, that makes.
He's adjusting. This is a nice question because it makes me think. Okay, so for any individual game, things are kind of random. So it would be really interesting to understand how many games do you need for the average to work out. So if it's a 3-game series, is that enough, or is it a 7-game series that's required to get enough more offensive zone possession to essentially win the series? It's interesting.
And yeah, the details that you're talking about are in the papers, so it's probably best if I leave them more to the paper. But a rebound, for example, there's no possession of the goalie, so that would be a continuation of team possession as long as the same team received the puck after the rebound.
And I think, but I could be wrong, Miranda would be the person to ask because she wrote most of that code. But I think the idea is that the possession in the ozone starts when you cross the line.
Yeah.
And so the time for the ozone possession starts at that point.
That's correct.
Have you tried to score adjust the model? Like, of course, when we are leading 3-1 and it's 2 minutes left, we will not try to have long attacks.
Yeah,
that's ozone. So I guess that's the randomness on a game level, that you have possession until you are in the big lead, and then you eventually let other team have the puck more.
Yeah, so I'm just thinking for a second because I think that's a great question and it's something we considered. We looked at possession across different strengths and we looked at possession across different goal differentials. So when you're leading and when you're trailing, what possession do you have, and how does that lead to better success? And so I'm just struggling to remember exactly what conclusions we drew, but they're not in the paper, so I probably shouldn't comment on them. But I think that it's a worthy analysis. As you're outpossessing the opponent, as you're leading your opponent, you might take some teams might have a strategy to, not possess the puck for as long, play a more dump and chase style and tire out the opposing team. So I think that's an area of research, not even how it correlates to success, but just what do possessions look like at different goal differentials is a really interesting area. So thanks, and I'll take it.
We should talk more because we looked at the data and didn't seem to find anything interesting or exciting, but we might not have been thinking about looking at it the right way.
Yeah, thanks.
Any other questions? So I mean, I think I follow up on the second last in terms of sort of how long of a playoff series. So I mean, now you looked at one season and a half a season. So can you give some insights into how, like, what is the reduction in correlation as you move to shorter and shorter sample periods? Like, where do you go, take the threshold from good to bad and so forth?
Yeah, it's a great question. So in order to figure that out, we included that in the most recent version of our paper. So we did a rolling analysis where, we took our data set and so, for this, for example, this shows you, I'll go to our stability slide. Wow, I had a lot of slides. This showed you that if you use half the data set, so 50%, the correlations, stand strong. But the question is, if you use just 1%, would the correlation between the 1% of data and the 99% of data still be as strong? So we did this by looking at the first 5%, 10%, 15%, and kind of kept looking at the first half and the first section and the second section. And we found that after 5 to 10% of the data set, so that's the equivalent of, I think that's like maybe 4 or 5 games per team. Depends because there's a different number of games for each team in the data set. But basically, after 5 to 10% of the games, the correlation kind of stabilized above 0.8.
Okay.
And so that's, I think, an interesting question because it's like, how many games do we need for robust analysis? We know with half the data set it is, but with a small number like 5% or a playoff series like 3-4 games, is your strategy going to be successful or should you throw it out the window? But we found that 5 to 10% of the data set, so 2 to 5% of a season, you could see that your strategy is already going to be indicative of future success.
Yeah, thank you. And then I was wondering, so I mean, now you, like previous work you described, have taken maybe more complex models, and you show that a fairly simple metric, but you can also imagine, okay, I just add a little bit of complexity to it, like I define the zone in some other way, or I weight the zone in some other way, or I take into account like the goal differential. What do you think is sort of the next thing that you would like to add in terms of complexity and to improve your model?
So I think it's tricky because one thing we liked about OZ-PTD was that it kind of encapsulates other stuff. Like whether you're able to enter the zone, controlled zone entries is something people talk about a lot. And that's hopefully captured in offensive zone. I would guess that, there's a correlation there.
Yeah.
And so we're thinking that it's almost like an amalgamator of other metrics. But I think in order to kind of increase the complexity a bit and maybe improve it, I would probably have some kind of, I mean, this is dream world, but I think what we wanted to do is have some kind of measure of the opposing team's ability to stop your possession, like their pressure. And so if you could have some metric that showed, this is our offensive zone possession differential. So we outpossess the opponent and the opponent's a really strong defensive team. So outpossessing, the Florida Panthers who are in the Stuck Cup final versus a lesser team, that should be weighted differently.
Yeah.
And so I think that would, maybe improve the results to kind of have some kind of team bias where you look at the strength of teams.
Yeah, no, it makes sense. And I mean, I can also imagine sort of combining it with some of the previous speakers' work where it matters where you control it in terms of probability of scoring, etc.
Yeah, even within the offensive zone, there's different points in the zone that are much more dangerous.
Yeah.
Yeah.
Thank
Thanks.
you. And any final question? Okay, so let's thank the speakers.